Next thing I'd like to discuss are, one of the things that we should be talking about is the moon, which is orbiting the Earth. And the moon also has, if we look up at the sky, and this was something that was obvious to ancient peoples, the moon has phases. They probably made up stories about what was happening to the moon. Maybe the moon was being gobbled up by something, and then if they were lucky and they prayed to their gods, there'd be a new moon. But what we know is that all we're seeing is the shadow. We're seeing various shadows that are falling on the moon. So at some point in time, the moon is completely blocked out. We have what's called a new moon. So at Rosh Chodesh, we look up at the sky, we don't see the moon at all. Then sometime after that, we go into, we form what's called a new crescent. So we have the new crescent moon, and then the crescent moon becomes a first quarter moon. And then so we go from the new moon, which is nothing, to the first quarter moon, and then we've got, then we go to what's known as the waxing gibbous moon, Gibbous. So the gibbous moon is, this is building up. I may have drawn this on the wrong side. I don't remember right now which way the moon. It's in your book. Okay, so chapter 2 is called the Copernican Revolution. So I want to talk a little bit about. We talked about what ancient man believed, what ancient man thought, and now I'd like to talk a little bit about how we got away from the misconceptions of ancient man. So the geocentric universe was a concept that was around for a very, very long period of time. Aristotle said that the Earth was at the center of the universe, and it seemed completely reasonable at the time that the Earth was a stationary thing and everything was rotating around the Earth. Now that idea was certainly explained in much greater detail by Ptolemy, who lived in the 2nd century of the Common Era, 140 CE. And what he and other people had determined was those that actually studied what they could see in the heavens were that there were some planets that the way they moved in the sky was they would seem to move from east to west. And we know now that this would be when because that wasn't known at the time. When the planets were closest to the Earth, they would move from east to west. But when they were further away from the Earth, they would seem to move west to east. So we had this what was called retrograde motion. And then some planets would switch to a prograde motion, and they would move west to east. So the ancients saw that Mercury and Venus did this. Now these were called inferior planets. But Mars and Jupiter and Saturn, and these were the only known planets at the time. So we had, besides the Earth, we had these other 5 planets: Mercury, Venus, Mars, Jupiter, and Saturn. But Mars, Jupiter, and Saturn, they moved in a different way. These were superior planets, and they made one prograde west to east revolution around the sun during each trip around the celestial sphere. So these were always prograde. And in order to explain this is very puzzling to ancient astronomers. So to explain this, they came up with the idea, the only way that they could account for the fact that some of these things seem to be going like this, and some of them would seem to change direction, had to do with the fact that these things, when they orbited the Earth, what they were doing is they were moving in something called epicycles. So if we look at just a single planet, let's say we look at the planet Venus, what we would see is so here's the Earth at the center of everything, and here's Venus. And Venus, rather than moving around the Earth like this, is actually moving around the Earth in such a way that it's actually rotating around some central point. So it's moving like this, and then it's rotating and it's rotating. And so it's actually tracing out a path that looks sort of like this as it moves around the Earth, this kind of spiral path. And this is called an epicycle. So it's forming these epicycles. Now that is kind of a bizarre sort of thing to actually have happen. And one of the things about scientific theories, one of the things that I didn't mention when we were talking about the theories, is that the best theories and the ones that are tend to be the ones that are the most tested in time are very, very simple theories. They don't have a lot of complications. During the 13th century, there was a gentleman by the name of William of Ockham, and he stated something that today is called Occam's razor. Entia non sunt multiplicanda praeter necessitatem. That Latin phrase means things should not be multiplied beyond necessity, which basically is a way of saying, keep it simple, stupid. Don't make things more complicated than they really need to be. And this is an example of an unnecessary complication. So if I have to go through all kinds of hoops, jump through hoops, in order to show some physical phenomenon, generally it turns out to be that there's a simpler explanation, and the simpler explanation is the correct explanation. About the scientific method, one other thing that I didn't mention about the scientific method, we were talking about its predictive value, that you should be able to predict things. I should have given this as an example. Einstein had his general theory of relativity, which was published in 1916. And one of the things that Einstein's theory said is that in the presence of a sufficiently high gravitational field, light ought to be bent. And he suggested that it might be possible to see this bending of light during a solar eclipse. It was 3 years later when the astronomer Arthur Eddington actually made the first determination of that. So Einstein's theory predicted this, and Eddington in 1919 was able to actually demonstrate the bending of starlight during a solar eclipse. The more distant stars, the light was actually shifted in position. So that's an example of that as well. But Occam's razor is another thing that kind of comes out of the scientific method. The things don't have to be complicated. And here they most certainly are complicated when we have to use epicycles. So epicycles were around for quite a long period of time. From the time of Ptolemy, we then had, and actually you needed to, if you wanted to show the movements of all these celestial spheres, you had to use 80 separate epicycles in order to be able to show all of this. Now, Nicholas Copernicus, who lived from 1473 to 1543, he actually had rediscovered something that had been suppressed by the Catholic Church, which was the Greek astronomer Aristarchus had what we would call today a heliocentric solar system. So Aristarchus believed that no, it's not the Earth that's at the center of the solar system, but it's actually the sun that's at the center of the solar system. So Aristarchus was actually able to demonstrate this, and it took many, many years before, as I said, this was rediscovered by Copernicus. Now, prior to that time, the church did a pretty good job of hiding all of these things, but the church probably set science back maybe about 2,000 years because of the fact that they just wouldn't accept physical evidence of the way the world really was operating, if it in some way contradicted church dogma. So it turned out that actually Copernicus published in 1543, right before his death, he published his realization that there was a heliocentric solar system, and took a while before the church actually got around to banning this. They didn't ban it until 1616, but it was banned until near the end of the 18th century, before the church actually recanted its position. Now, other people that sort of did work that led to the demise of the geocentric solar system were people like Galileo, and he really pretty much, I think, put the nail in the coffin, so to speak, because Galileo, in the year 1609, Galileo Galilei actually built the first telescope. And with that telescope, he was able to focus this on things like the moon and Jupiter, the planet Jupiter, and the planet Venus. And what he saw when he looked at the moon was he saw craters, and he saw mountains, and he saw features very much like those of the Earth. Not these this flat disk kind of idea that was actually promulgated by the ancients. So he also then looked at Jupiter, and he noticed that there were 4 objects whose position changed throughout a period of time, and they seemed to be actually orbiting or moving around the planet Jupiter. So this change in position actually gave rise to the idea. But basically, what's happening is the planet is the moons were actually orbiting Jupiter, and what Galileo realized was that, well, wait a minute, if the Earth is actually at the center of everything, why aren't they orbiting the Earth? Why are they orbiting Jupiter? So that gave him some pause. Then he looked at Venus, and he saw something else very peculiar about Venus. He noticed that Venus was actually, what was happening with Venus was, just like when we look at the moon and we see the quarter moon and the gibbous moon and the full moon, etc. He noticed that Venus, the surface of Venus, was also undergoing these phases, and he realized that this had to do with the fact that Venus was actually rotating, and just like the Earth's moon was rotating around the Earth, and we were getting these various aspects of that because of its position relative to the sun. He realized that the only way that you could really account for this was that the sun would actually have to be at the center of the solar system and not the Earth. So it turned out that the individual who actually finally eliminated the idea of the epicycle was to come soon after that. Tycho Brahe was a Danish astronomer who lived from 1546 to 1601. So unfortunately for him, he died about 8 years before Galileo invented the telescope. So Brahe actually had to do all of his observations just visually, that is by using his eyes. And he nevertheless collected a huge amount of astronomical data that was very, very useful to an assistant that he hired by the name of Johannes Kepler. And Kepler is the individual to whom we can attribute the complete and total destruction of the idea of epicycles, and also Kepler's work, which is still very accepted today, gave rise to a lot of the modern theories that we have regarding the way the solar system actually does function. And Kepler, there were 3 laws that Kepler came up with. First of all, prior to Kepler, it was assumed that all objects, even once people recognized that they were orbiting the sun rather than the Earth, that is, we had the heliocentric solar system, they still assumed that everything orbited the sun in a perfect circle. And Kepler said not so. He said that the orbits of the planets are elliptical, not circular, which is what Copernicus had proposed, that they were circular. And if you look at an ellipse, so here's a circle, and you could think of an ellipse as being a flattened circle. So if I push on this, I'm going to flatten it out, and I might get something that looks like that. If I pushed on it enough, I could actually flatten it into a straight line. So we talk about an ellipse as having what we call eccentricity. And the eccentricity of the ellipse has to do with, well, for instance, the eccentricity values are between 0 and 1. So if the eccentricity is 0, it's a perfect circle. If it's 1, it's a straight line. It's been pushed into, so anything in between that is going to have some value between 0 and 1. It's going to be something that we would actually recognize as an ellipse. Now, it turns out that for most planets, the numbers are a lot closer to 0, so I'm showing a much more flattened ellipse. I don't know yet what the eccentricity of this would be. It's probably maybe less than 0.5, but these things still were not perfect. They were not perfect circles. They were ellipses. Now, an ellipse, the other property that an ellipse has is, a circle has one central focus, the center of the circle. But there are actually two foci, plural focus. So there's two foci in an ellipse. And what the first law that was proposed by Kepler was that the orbits of planets are elliptical, and the sun is actually at one of the two foci. So we'll put the sun over here. So one elliptical paths and sun at one focus. Now, as this thing gets closer to 0, the two foci get closer and closer together until they actually merge. When you get to 0 and you have a circle, then you only have one focus. Okay, so that was the first thing. The second thing that Kepler said was, I want to draw this a little bit bigger so you can see this. So again, let's draw our ellipse. And here's our ellipse. And what Kepler said was that, and let's put the sun over here. This, again, as I said, is very exaggerated, but just to make this a little bit easier to see. So what Kepler said was that if you've got an object orbiting, whether it's the sun or some other object, if something is orbiting a more massive object, it's going around it like this, and we see how far it moves over some period of time, let's call that T1. So this is the starting point, and this is the ending point here. So this is this would be a T0, this would be T1 here, this entire period here. What he said was that if you looked at the position here and you drew a line to the sun, and then you looked at the position here and you drew a line to the sun, that the area in here that is actually enclosed within that orbit is going to be equal to the area. If I take any other position along here and I go from a T0 to a T1, or from a T0 to a T2, where T1 and T2 are the same time period. So now let's say I'm going to come out to, I'm going to be over here at T1, and this will be T2. What Kepler said, and then I'm going to do the same thing, I'm going to draw a line back here and a line over here. And what Kepler said was that if you were to actually measure the areas in here, so this one we'll call area 1, A1, and this will be area 2. Kepler said that if T1 and T2, that's the time that it took to go from here to here, is T2. If T1 equals T2, that is in the same time period, that you will that this satellite will sweep out equal areas in that time period, regardless of where we happen to measure along its path. So A1 is going to be equal to A2. And that was a very, very interesting proposal, because it also is something that's actually very, very useful as well, because it turns out that if you're piloting a spacecraft, this is something that you can use, and it actually has been used a number of times when the original Voyager spacecraft was sent out of the solar system. What scientists did in order to give it greater propulsion was they would actually loop it around some of the large gas giants like Jupiter and Saturn. They would actually move it close to the planet and have it pick up speed, because you can see that when you're out here and you're going at a certain speed, you're not moving very, very far. You're moving much, much further as you get closer to the planet. This is called the slingshot effect. So actually they use this slingshot. This was back, I think, in the 1970s when this object was launched, and it's probably been a decade or more that it actually left our solar system, and God only knows where it is right now. I don't even know that they're still picking up signals from it, but it's very, very far removed from the Earth at this point in time. And so that gave it some greater velocity. Another example is the Apollo 13, what was supposed to be a lunar landing that actually went bad. They had gotten, going from the Earth to the Moon, somewhere several days along in the trip, there were a series of accidents that occurred on board the Apollo, and it turned out that they actually had to get into the lunar lander and eject the rest of the spacecraft, and were able to return home. But they were only maybe 2/3 of the way or 3/4 of the way to the Moon, and a decision had to be made when this thing was at that position with respect to the Moon. Here's the spacecraft, and a decision had to be made whether to just turn this around and go right back to the Earth, or continue out to the Moon and swing around the Moon, use the slingshot effect to pick up additional velocity. And calculations were made to show that by going the rest of the way to the Moon, they would pick up enough additional speed that they would actually get back to the Earth faster. So that was a very useful maneuver. So that's the second part of that. The third part of this is, and the last part, is actually so we've got the equal areas and equal times, the sun being at the center of a focus in elliptical orbits. And the very third part of this thing was that if you looked at the period, which is the amount of time that it took to make one revolution around the central object, if you looked at that in years, the square of that value in years is actually equal to, if we look at the distance and what are known as astronomical units. And an astronomical unit is the distance. Here's the sun, here's the Earth. The average distance from the sun to the Earth is 1 astronomical unit, 1 AU. And so if we measure this in astronomical units, that's going to be that distance cubed. So P squared is equal to A cubed. In actuality, there's a formula that you'll find in most physics books that actually describes more accurately this relationship, and that is that T squared, which is still the period. We don't use usually don't use P for a period. T is capital T is the time, and this is in seconds, not in years, which is kind of an arbitrary designation. But T squared in seconds is equal to 4 pi squared r cubed, r being the distance from, from the, whether it's an astronomical unit or whatever, but this is in meters. The distance in meters from the orbiting object, that's r, and that's divided by g, which is a constant called the universal gravitational constant, times m, which is mass in kilograms. So, and this is the mass of the object being orbited, not the mass of the satellite, but the mass of the central object. And you can actually use this equation to give you the time in seconds of of one period, of how long it takes to go around, let's say, around the sun. So you can do that you can use this to actually calculate how long it takes any planet to make its orbit around the sun, for instance. Now there's one other thing that I want to mention, which is Newton, and then we'll finish up with Isaac Newton. And Newton's laws of motion, coupled with a gravitational law, and I'm going to mention, I didn't tell you what G was, but we're going to see G again in a minute, that capital G. This was all stuff that Isaac Newton, a tremendous genius, came up with. So Newton, there were 3 laws of motion. The first one is sometimes referred to as the law of inertia. And what Newton said was that if an object is moving, if an object is not moving, it's going to continue to not move unless it's acted upon by some outside force. And if it is moving, it's going to move in a straight line unless it's acted upon by some outside force. So whatever kind of motion that you have, for instance, if an object is orbiting, now we can do something, we can do a kind of a simple thing. We put our body in here and we have a string and we've got a weight and we're swinging this around our body. And if we were to cut the string, what would happen is, if we cut it right here, it would go, the object would not continue to go around in a circle, it would go straight wherever we cut it. If we cut it over here, it would move along its, what we call tangential velocity, along the tangent of that line, and it would continue to move in this direction. So it just depends on where we happen to cut it. The fact is that objects actually would do that in space if it weren't for the fact that there's gravitational attraction between one object and another. So the planets ought to just be moving in straight lines, except that they're being pulled in towards the sun by gravity. So we have this force going this way, and that causes this curved path that the planets take. So that was Newton's first law, the law of inertia. And I'm going to skip momentarily to his third law, which is the law that sometimes is known as action-reaction. And it's simply stated that every time there's an action, like a force that's applied to something, there's an equal and opposite reaction. So when I push down on the floor because of my weight, the floor is simultaneously pushing up against me. So that's an action, what we call an action-reaction pair. And the second law, which is the one that we actually have a mathematical equation for, is force equals mass times acceleration. It's not the way that Newton originally formulated the law, but for purposes of what we're going to be discussing, that's the form that we're going to use. Force equals mass times acceleration. So Newton, there was a fourth law, not a law of motion, but Newton's law of gravitational attraction, and I'm going to show that law as well. And that says that force is equal to G, there's that big G again that we saw, M over R squared. So what this is saying, I've got two objects, a smaller and a greater object. They could both be the same. We could have used M1 and M2, it doesn't really matter. But I'm using this because I'm going to derive something in a minute. It just makes it a little bit easier to understand this way. So we'll call the large M the central object, the object that is actually being orbited, and the smaller one its satellite. And G is a constant, is a universal constant. Everywhere in the universe it's going to have the same value, and that is, I should have G memorized. It's 6 point something, I heard it, 6.67. Couldn't remember that. 6.67 times 10 to the minus 11th Newton meters squared or kilograms squared. Now, the Newton is a unit of force. It's equal to 1 Newton is 1 kilogram meter per second squared. That's a 6 there. And so if you take that value, the mass in kilograms of these two objects, and the distance in meters, that will give you the force. And you can calculate the force in newtons. And so we now have two different ways of expressing this. There's one other equation that I want to introduce, and that is acceleration, or angular acceleration, is actually equal, when something is orbiting this way, it's going to be equal to its tangential velocity squared, divided by, divided by r, that radius, that distance that it is from the orbiting object. So having said that a equals v squared over r, I can now substitute into this equation a equals v squared over r, and that's going to give me force is equal to m v squared over r. But I also know that force is equal to gmm over r squared. So now I can say that that is equal to gmm over r squared. My m's are going to cancel out. I've got m's on both sides of the equation. And now I can rewrite this expression as v squared over r equals gm over r squared. I want to get rid of the r on the left side of the equation now. So I'm going to multiply both sides of the equation by r, which tells me that v squared is going to be equal to gm r over r squared, and then that's going to cancel out, which is going to give me gm over r. So v squared equals gm over r. The velocity is going to be equal to the square root of the gravitational constant times the mass of the orbiting of the central object divided by the distance that the satellite is from that object. And from this, we can actually calculate a lot of really neat things. We're going to see later on, we're going to be using this equation time and time again. But when we talk about black holes, we'll be able to use this equation to establish the size of a black hole, how massive, if we know that a star had a certain initial mass, we can calculate something called the Schwarzschild radius, which is its size when it collapses, to how big it will be once it collapses to a black hole. There's a lot of neat stuff that we can do with this. So we'll talk about that later on. Anyway, that concludes, I believe. I just want to check my notes here and see that I've got everything, that I've given you everything that I wanted to talk about here. I think so. And that will conclude today's presentation. I wish you Hatzlacha for your exams and everything that you do in the Jerusalem Science Contest, and we'll see you next week. Thank you.